Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to this channel and hit the bell icon to get notified when I post my new videos. So today I'll be discussing how to analyze and how to determine the slope and deflection for a overhanging beam using moment area method. So I have a numerical over here wherein ACD is the overhanging beam, wherein AC is the simply supported part and CD is the cantilever part, and AC is the simply supported part which is loaded with a center concentrated load of magnitude equal to 20 kilonewton, and it is located exactly at the distance of 2 meter from A and that of C also. And whereas in case of cantilever part, it is having the 5 kilonewton load exactly located on the free end, that is at point D, and which is at the distance of 2 meter from point C. So we are supposed to determine what is the slope and deflection at the free end of the overhanging beam. So that is at point D. So now, before determination of the slope and deflection, so first and foremost step is that we are supposed to determine the support reactions. So we have the two supports here. So first one is A and second one is C. So here, in order to determine the support reactions, we are supposed to apply the or we are supposed to make use of the application of the equilibrium conditions. So basically there are three equilibrium conditions, that is sigma H, V and M. So here first equilibrium condition is that the summation of all the horizontal forces is equal to 0. So here you can just observe there are no horizontal forces, so therefore automatically the first equilibrium condition is satisfied. So coming on to the second equilibrium condition, that is summation of all the vertical forces is equal to 0. So we have the totally the four vertical forces over here. So two support reaction, that is VA and VC, and then two external loads, that is 20 and 5 kilonewton. So I just take the sign convention as upward forces are considered to be as positive and downward forces considered to be as negative. So with this sign convention, if I want to proceed, so sigma V will be equal to 0. So VA plus VC is equal to 20 plus 5. That is, I have equated upward forces is equal to the downward forces. So VA plus VC is equal to 5 kilonewton, 20 plus 5 kilonewton. So totally it will be 25 kilonewton. So coming on to the next equilibrium condition, that is moment, the equilibrium of moment, algebraic sum of all the moments about any of the point is equal to 0. Since we are in the determination of the support reactions, so therefore the moment has to be considered exactly on the support itself. So since there are two supports over here, A and C, so we have the liberty to take the moment by taking A or C as a reference, not at the intermediate points. So therefore with that I have taken moment about A as a reference point. So therefore before proceeding to the moment equation, I just consider the clockwise moment as positive and anti-clockwise moment as negative. So with this sign convention, if I want to proceed, so I just start from point D over here. So 5 into the distance between D to A is 6 meters. So 5 into 6. So go along the force through the line of action. It is the clockwise. Hence it is considered to be as positive. Hence it is considered to be as positive. So next thing is point C. So VC into the distance is 4 meters. So VC into 4, we need to go along the line through the line of action, go along the force through the line of action. It is in the anti-clockwise direction, hence it is considered to be as negative. So VC into 4. So next is point of 20 kilonewton. So 20 into the perpendicular distance acting is 2 meters. So here 20 into 2. So we need to go along the force through the line of action. So 20 into 2 will be in the clockwise direction. Equate this to 0. We'll get the value of VC as 17.5 kilonewton. 17.5 kilonewton. So after getting the value of VC, so if I just equate this in the equation of the vertical equilibrium condition, so I'll get the value of VA as 7.5 kilonewton, that is 25 minus 17.5, that is 7.5 kilonewton. So this is all about the determination of support reactions by using the equilibrium conditions. So next is determination of bending moment and sketching of the bending moment diagram. So this is a very important step in determination of slope and deflection. So first and foremost thing, before solving for the bending moment diagram, I have the sign convention here that if I just calculate the bending moment from right to left, so I need to consider anti-clockwise moment as positive and clockwise moment as negative. So, and again in the left hand side, if I want to proceed, so this sign convention will be in the reverse direction. So that is clockwise will be positive and anti-clockwise is negative. So but I'm going from right to left, means in this particular example I'm going to calculate from D to A, means right hand side to left hand side. So therefore I'll just take the sign convention as anti-clockwise to as positive and clockwise as negative. So with this sign convention, if I just proceed it, so starting from point D, so next point will be point C. So 5 into 2 will be 10 kilonewton. 5 into 2 is 10 kilonewton. It is in the clockwise direction. So right hand side clockwise is negative. So it is in the downward direction. So next is next point is point B. Point B. So therefore from point D we have 5 into 4, 5 into 4, and then VC into, here we have VC, so VC into 2, 5 into 4 and VC into 2. So 5 into 4 it is in clockwise direction, and VC into 2 it is in anti-clockwise direction. So anti-clockwise is positive and clockwise is negative. So we'll get it as 20 minus 17.5 into 2. So therefore we'll get the value as plus 15 kilonewton meter. So therefore it is drawn above the baseline. So since we have the one more point we have is point A. So exactly at point A, previous to point A, we have 3 points, 3 loaded points particularly. So that we are supposed to consider. So first thing is 5 into 6. 5 into 6 from D to A, it is clockwise. Hence it should be considered as negative because we are going from right to left. So next thing is VC into A, VC into 4. So VC into 4, it is in anti-clockwise direction, hence it is considered to be as positive. So next 20 into 2. So 20 into 2, it is again in the clockwise direction, hence again it should be considered as negative. So if I just substitute and simplify all this, I'll get the value as 0. So since we have this bending moment diagram only with reference to the concentrated loads, hence it should be in the linear variation, and hence I have drawn it as a straight line itself. So this is all about the bending moment diagram. So here in some point between B and C, you can just observe over here the bending moment is passing from positive to negative value, and at some point it is 0. So the bending moment point wherein the point of the baseline wherein the bending moment is equal to 0 is called as point of contraflexure. Contraflexure. So point of contraflexure, it is a point where bending moment is equal to 0, or it can also be taken as the point where the bending moment changes from positive to negative or vice versa. So it is also called as point of inflection. Point of inflection. So point of inflection or point of contraflexure is a point wherein the bending moment is equal to 0. So here I know the distance between B to C as 2 meters. So if I want to calculate the point of contraflexure from C, I just take it as x, and I know the total distance as 2 meters from B to C. So here the from B to the point of contraflexure, it will be 2 minus x. So if I want to determine the value of x, so if I want to determine the value of the point of contraflexure, I make use of the similar triangle. So I make use of the similar triangle method. So wherein that is nothing but this triangle, that is the of base equal to 2 minus x, and for the base equal to x. So it is 15 divided by 2 minus x is equal to 10 divided by x. So here 10 is in the negative direction. You can neglect the negative convention. So since it is the calculation of distance, so we can just neglect the negative direction. So it is 15 divided by 2 minus x is equal to 10 divided by x. So therefore the x value is equal to 0.8, and this value is equal to 0.8 we have got, and from B it will be 2 minus x. So it is 2 minus x means 2 minus 0.8, it will be equal to 1.2 meters. So 1.2 meters from B. So this is all about the calculation of bending moment, sketching of bending moment diagram, and then the calculation of distance of point of contraflexure. So coming on to the next step is that determination of deflection at point C. So before why I am interested in determination of deflection at point C means, so I need to calculate a slope at point A. So if I want to calculate slope at point A, I need to calculate deflection at point C. Why? Because it makes me to solve with the easy calculation. So I need to calculate deflection at C. So here you can just observe here. So wherein I have just drawn the deflected position of the beam in the red color dotted line. So from A to C it is sagging, it is a sagging style, and then from C to D it is in a hogging fashion. So I have also drawn a tangent which is represented by the green color line which is passing through the sagged portion of the beam. So that tangent, if it is adjacent to point C, then the deflection made by point C with that of the effect of the external application of the load, it will be termed as DCA, and that of D it is termed as DDA. Deflection at point C is DCA. So therefore deviation or deflection at C is nothing but deviation, that in order to find out deviation C with reference to A, it is called as deflection at C with reference to A. So here by using the moment area theorem, if I want to solve it, the deflection will be taken as area between C to A, and multiplied with the centroidal distance with C as a reference point. So remember, if I am going to take the deflection, if I want to calculate the deflection at point C, so the point of reference for calculating the centroid will be same as that of the point wherein we are going to calculate the deflection. So here in this particular step, we are going to calculate the deflection at point C, means the point where we need to calculate the centroid will be exactly from C as the reference point. So therefore, we have the area multiplied by the centroidal distance between C to A. Here we have between, if I just take the reference of the bending moment diagram, we have three triangles between A and C. So first one is the triangle with 2 meter span of the base, and second one is 2 minus x base, and third one is the base of x distance. So therefore, if I just take the area of the first triangle, it is half into half is mentioned as 0.5 over here. So half into 2 into half into 2 into 15. So this is half into 2 into 15, and then half into 2 into 15, we are taking centroid. It should be multiplied the area with that of centroid. So we are taking centroid with reference to point C. So therefore, here it is the triangle 2 meters 15. Okay, so here we have C point at a distance of 4 meters from that of B point. So therefore, we have the centroid, we have a centroid. If I just pass the centroidal axis over here, so this distance will be equal to 1/3 of 2. So it will be exactly at this level, but we need to add the remaining distance which is reaching to point C. So that is nothing but 4 meters. So it should be equal to 1/3 of 2 plus 2 meters. It is 2 meters. Sorry, it is 2 meters. So 1/3 of 2 plus 2. So this is all about the calculation of area multiplied by the centroidal distance with reference to the first sketch. So coming on to the second sketch, I have the second sketch like this. So this is 15, and this is 2 minus x, that is nothing but 1.2 meters, and this is C point, so which is at the distance of x. So now if I want to proceed, so area of the triangle is half into 1.2, that is base is 1.2 into 15 is the height. Now if I just take the centroidal axis, so this is the centroidal axis. So from here it is 2/3 of the base. So 2/3 of base is 1.2. So it is 2/3 of 1.2 plus the distance which is touching the point C. So the remaining distance will be x. So therefore 2/3 of 1.2 plus 0.8. So that is the centroidal distance. With reference, this is the calculation of the deflection and the centroidal distance for the second sketch. And coming on to the third triangle, it is of this fashion, x, and this is 10, and this is point C. So here if I just draw the centroidal axis, so from C I am supposed to take, so from C it is 1/3 of the value of x. So the area will be equal to half into base is 0.8, and height is 10. So multiplied with the centroidal distance as 1/3 of x. X is 0.8. So since here it is the negative variation of the moment, so I have taken it as the negative sign convention over here. So this is all about the calculation part of the deviation of the point deviation at point C. So if I just simplify all the things, I'll get the value as 53.33 divided by EI. So this is the calculation of deflection at point C. So coming on to the next thing is slope. So here I told you that in order to calculate this easy calculation for the slope, we need to calculate the deflection. So at point C. So I have a triangle over here ACC1. So I have taken the triangle ACC1 over here. So if I just project that triangle here, it will be as ACC1. So ACC1, CC1 is nothing but the deviation DCA which I have got, and this is theta A, which is the angle subtended due to the deflected position of the beam, and the distance between A and C is equal to 4 meters. So if I just want to calculate the theta A part, so that thing can be used by the application of tan theta, tan trigonometric function. So tan theta A will be equal to DCA divided by 4. DCA, opposite by adjacent, DCA divided by 4 meters. Since theta is very small, so tan theta A can be equated as theta A itself. So by the previous slide calculation, I have got the DCA value as 53.33 divided by EI. Substituting that, and I'll get the value as theta A as 13.33 divided by EI. So this is all about calculation of slope at point A. Now, the next step is I need to calculate the slope at free end. So slope at free end is nothing but I have the deflected position here. At A, I have theta A, which I can observe here. So with reference to D point, it is theta D here. With reference to D point, it is theta D here. So by making use of moment area first theorem, so we have two theorems as in case of moment area method. So first theorem is for slope calculation, and second is for the calculation of deflection. So as in case of slope, as in case of theorem 1, I just make use of theorem 1 here for calculation of the slope at the free end. So here theta A minus theta D can be equated as area of bending moment diagram between A to D point, divided by EI. So if I just take the reference of the bending moment diagram, so I have the individual figures as 4 triangles between A to D, 1, 2, 3 and 4. So 4 triangles. So here I need to take the area of all the triangles into consideration in order to calculate that. So coming on to the first triangle, with A, B and 15 with base as 2 meters. So it is half into 2 into 15, half into 2 into 15. So next, coming on to the next triangle with 15 and 2 minus 6, 15 and 2 minus 6. So 2 minus 6 is 1.2 and this is 15. So half into 2 minus 6 into 15, half into 2 minus 6 into 15. So next, coming on to the next triangle, that is X as a base and height as 10 kilonewton. So it is in the negative direction, so it is minus half into 0.8. The value of X which I have got, it is 0.8 into 10. So next triangle is 2 meters with the base distance CD. So again it is going in the negative direction, hence it is considered to be as minus. So half into 2 into 10. So this is all about the calculation of area of the bending moment diagram between A to D for calculation of the slope at the free end D. So if I just substitute that, theta A, I have got the value as 13.33 divided by EI from the previous slide. So if I substitute that and simplify all the things, I'll get the value of theta D as 3.33 divided by EI. So this is the value of slope at free end. So this is the next step which is regarding to finding the deflection at point D. So here the deflected position at CD is going in the upward direction. So therefore, the exact deflection at point D is DD2. DD2 is the exact deflection at point D. So therefore, I need to determine the exact deflection at point D, means it is nothing but DD2 value I need to find out. So DD2 is nothing but minus DD2. Why it is minus sign? Because it is going in the upward direction. Due to the hogging nature of the bending, it is going in the upward direction, hence it is taken as negative value. Minus dd2 is equal to d d2 d1 minus d2 d1 minus dd1. So d2 d1 minus dd1 you will get the value as dd2. So if I just substitute d2 d1 will be considered to be as deviation of d with reference to a. Deviation of d with reference to a, and dd1 is the it could be taken as the arc of the circle, and then it is nothing but the product of span multiplied with the angle created. Span from A to D is 6 meters and angle created is theta A. So therefore it is 6 times of theta A. So after all these things, so deviation of D with reference to A is nothing but area between A to D multiplied with the centroidal distance with D as the reference point. So minus that of 6 times of theta A. So therefore, if I just calculate the area between A to D, it is comprises of 4 triangles. So if I just start from the first triangle, that is 15. So this is 2 and this is A, and different distance here from D is A to D is 4 meters. So starting from the point here, so this is the centroidal axis. So from here to here it is 1/3 of the base, 1/3 of 2 meters. So plus the remaining distance is 4 meters. So the area will be, the area which I have written here is half into base is 2 meters, height is 15 into 1/3 of 2 plus 4. So this is all about the calculation of the area and centroid for the first triangle. So coming on to the next triangle, so it is 15 here, 2 minus x is 1.2, and the distance from here towards D here is x plus 2.8, x plus 2, that is 2.8 meters. Now, so if I just mention this as a centroidal axis, so the distance from here to here will be 2/3 of 1.2, 2/3 of 1.2. So I have got the distance until here, but my reference is until point D. So we need to add with reference to the remaining distance as 2.8. So the area will be half into 1.2 into 15 into 2/3 of 1.2 plus the remaining distance is 2.8. So coming on to the next triangle, it is x is 0.8. I have 10 kilonewton, and this is point D, and the distance is 2 meters. So the distance is 2 meters. So here if I just draw the centroid axis, so this is a centroidal axis, so this is a centroidal distance, so it is at 1/3 of 0.8. So it is at a distance of 1/3 of 0.8 plus this remaining distance is 2. So therefore it is in the negative fashion, so I have taken it as negative. Half into base is 0.8 into 10 into 1/3 of 0.8 plus 2 meters. So the last thing is for the next triangle or the last triangle, which is at the base of 2 meters. So this one, so it is half into 2 into 10 into, if I just draw the centroid, it is exactly at the distance of 2/3 of the base. So 2/3 of base is 2 meters. So 2/3 of 2 meters. So this is all about the calculation of the area multiplied by the centroidal distance for the individual triangle. So if I just simplify this, and also I have 6 times of theta a to be subtracted with overall this. If I just simplify all the things, I'll get a deflection at a point D, that is d2 as minus 0.02 divided by EI. So I again repeat, the negative value will be considered because the deflection is going in the upward direction due to the hogging nature of the bending. Thank you for watching. Please like, share and subscribe the video. Thank you.